Hi guys. So now that we know what parametric equations are and kind of how they work, now we're going to introduce the calculus. All right, so now we're going to see, can we take derivatives of parametric equations? Yes, we can. So we can find slope, we can find concavity, we can deal with tangent lines, and we'll also take a look at integrals, but really the only thing we're going to do with integrals here is arc length. We're not going to do area, we're just going to look at arc length. So it's just minor things that we're doing with parametric equations, not everything. All right, so slope is still dy over dx. Right? It always is going to be the change in y over the change in x. But with parametric equations, y is a function of t and x is a function of t. So we find dy dt, we find dx dt, and we just divide. All right? So the first derivative, not so bad. So like for instance here, we want to find dy dx if we have x equals sine of t and y equals cosine of t. So dy dx equals dy dt over dx dt. So the derivative of y, derivative of cosine, is negative sine of t. And the derivative of x, derivative of sine, is cosine of t. Right? We can simplify this. Remember, sine over cosine is just tangent, and we still have this negative sign, so we'd say this is negative tangent of t. All right? And there's our derivative. All right? So we don't get a system of equations. We just get the one equation for our derivative. All right? If we want to find a second derivative, that's when things get a little funky. So if we take the derivative of dy dt, which you can see here is dy dx, which you can see here is a function of t, we're going to get a d squared y over dt dx, which is not what we want. We want dx squared on the bottom. So what we do is we divide by another dx dt, and that ends up canceling out the dt's and gives us the dx squared on the bottom like we want. Okay, right? Because this is the second derivative. All right, so we want to take the derivative of this guy. So we want the derivative with respect to t of negative tangent of t. And then we want to divide by the derivative of x with respect to t, which we've already found before, which was cosine. All right, derivative of tangent was secant squared. So we've got negative secant squared of t. All right, if we want, we can bring this cosine up. So you can say cosine is 1 over secant, and we're going to get negative secant to the third of t, or we could bring the secant down and we'd have 1 over cosine, negative 1 over cosine to the third of t. Either one of those is fine. And there's our guy, second derivative. All right, so that's how we find derivatives. So remember, divide the two functions, dy dt and dx dt for the first derivative. For the second derivative, we take the derivative of the dy dx with respect to t, and then we divide by another dx dt. All right, so here we go, find the slope. That's dy dx. And the concavity, that's d squared y dx squared at the point 2, 3. So it's in terms of x and y here. All right, well, we could just go straight to finding what a t value based on that. Like if x is 2, then t would be 4, it looks like. So this point gives me t equals 4. Of course, does that work here? Yeah, I think that works here. Yep, 16 minus 4 is 12. 12 divided by 4 does give us 3. Yep, so t does equal 4 from that point. Cool. All right, so now to get the first derivative, dy dx, I want dy dt over dx dt. Right? dy dt is the derivative of this guy. So I'm going to say this is 1/4 t squared minus 1 if I just distribute the 1/4. So it's much easier for me to take the derivative of that and just bring down the 2. I get 2/4 or 1/2 t. If I take the derivative of x, let's see, I can write this as t to the 1/2. So then it'd be 1/2 t to the negative 1/2, to the 1 less exponent. So the 1/2s are going to cancel. Cool. I can bring this up, and then we got t to the first and t to the 1/2 is going to give us t to the 3/2. So there is our first derivative. If we want to find the slope, we plug in 4. So when we plug in 4 there, we get that dy dx when t equals 4 is equal to 4 to the 3/2. So that'd be the square root of 4 cubed. Square root of 4 is 2. 2 cubed is 8. So our slope at that point is 8. All right, and we can use that to find a tangent line if we wanted to. We could use the point and the slope here, like this point, this slope. We can say y minus 3 equals 8, x minus 2, like that. That's the tangent line. All right, but it's back in rectangular coordinates, which is fine. All right, if we want to know our second derivative for our concavity, we've got to take the derivative with respect to t of our first derivative, which is this guy, which is not a hard derivative to take, and then divide it by another derivative with respect to x, which was this guy with the 1/2. So for this guy, the top, I bring down the 3/2. I get t to the 1/2. On the bottom, I'm going to have another one of these. So I'm going to have 1/2 t to the negative 1/2. All right, so 3/2 divided by 1/2 is going to give us 3. T to the 1/2 divided by t to the negative 1/2 is going to give us t to the first. All right, so there's our second derivative right there with respect to t. All right, and if we want to know that dy squared, oops, d squared y is how we write that, not dy squared. Oops, did it there too. Over dx squared at t equals 4. We just plug in 4 there. We get 3 times 4 is 12. So it's positive. So that means our function would be concave up at that point. Probably in an interval around that point, but you know. All right. So that's the basics of how we take derivatives with parametrics. All right, so let's look at now tangent lines at a point. So interesting thing about parametric equations is they're not necessarily functions, so they can cross each other again at the same point. Like this parametric equation right here crosses the point 0, 2 twice, at least. All right, it might keep going around and keep going around and keep going around. It happens a lot with sine and cosine in there. All right, so we want to know, given the equations, and they cross themselves at the point 0, 2, find the equation of both tangent lines at that point. All right, so pretend we don't have the graph, but we do know they cross there. So that means 0 is equal to 2t minus pi times sine of t. That's not like an easy equation to solve. Like, you get 2t over pi equals sine of t, but it's still, we have t's on both sides. Not easy to solve. All right, if we do the same thing with cosine, say, okay, it's y, so it's got to be equal to 2. Remember x and y. So we'd say 2 equals 2 minus pi cosine of t, divide by, or so sorry, subtract the 2, divide by negative pi. This is a much easier equation to solve, right? If we solve this, this happens every time. Let's see, pi over 2, 3 pi over 2, 5 pi over 2, and so on. It also goes back the other direction, negative pi over 2, negative 3 pi over 2, and so on in the other direction. So now we want to know which of these t values will make this equation up here true. All right, if I plug in just pi over 2, that's the first one, that's actually going to work. All right, if I plug in pi over 2, I'm going to get here 2 over pi times pi over 2 times, or sorry, equals sine of pi over 2. And this just cancels out over here and gives me 1, and sine of pi over 2 is 1, so this guy's good. If I go to keep going forward, 3 pi over 2, I don't think it's going to work. So I got 2 over pi, 3 pi over 2. Does that equal sine of 3 pi over 2? All right, well here the pi's cancel, the 2's cancel, I get 3. But sine of something never equals 3. All right, sine just goes back and forth between 1 and negative 1. In fact, at 3 pi over 2, it's negative 1. So that doesn't work. And in fact, if I keep going to the bigger numbers, this side over here is just going to keep being like, it's going to be 5 and then 7 and so on. Let's try to go backwards in the other direction. So let's try negative pi over 2. All right, so if we plug in negative pi over 2, we've got, let's see, 2 over pi times negative pi over 2. Does that equal sine of negative pi over 2? Well, everything's going to cancel out over here and just leave me with negative 1. And this does equal negative 1, all right, because sine is going down there, so it also equals negative 1. So that checks out. So those are the two guys where it crosses this point 0, 2. So now I've got the t values. Now I can find the slopes at that point, and that's what I need for tangent lines. I need slopes and points. We've got the point, we need the slope. All right, so we now can find dy dx, which is dy dt over dx dt. So the derivative of y with respect to t, the derivative of 2 is 0. We get negative pi times derivative of cosine is negative sine, so we get pi times sine of t on top. On the bottom, derivative of x, derivative of 2t is just 2. Minus derivative of sine is cosine, so we get pi times cosine of t. All right, so there is our derivative with respect to t. So we try pi over 2. I'm going to switch up some colors here so we don't get confused where we are. So for x equals pi over 2, we get that our dy dx, our slope, is equal to, we plug in pi over 2, we get pi, sine of pi over 2 is 1. 2 minus pi times cosine of pi over 2 is 0. So we get pi over 2, strangely enough, also for our slope there. So then the equation of the line there would be y minus 2 equals pi over 2 x minus 0. All right, so there's one equation. All right, you can simplify that if you want. You'd be like y equals pi over 2 x plus 2. That also is okay. For our second equation, let's go green here. We've got x equals negative pi over 2. So then our slope is, we're plugging in negative pi over 2 here. So we get pi, sine of negative pi over 2 is negative 1. So pi times negative 1. 2 minus, and cosine of pi over 2 is again 0. So pi times 0. So we get negative pi over 2 as our slope there. So we get y minus 2 is negative pi over 2 x minus 0. Or, so that's one way. Or we can say y equals negative pi over 2x plus 2. Notice they both have this same plus 2. That's the y-intercept of both of these tangent lines. And the tangent lines are drawn in here in blue. And they do cross each other. One of them is just the positive pi over 2 slope. The other one is the negative pi over 2 slope. Neat how that works out. All right, so that's how we can find tangent lines and tangent lines that cross each other. All sorts of fun things happening there. All right, the next thing, and I will do the integrating here on the calculator, all right, because it uses trig identities that we haven't really worked with much. All right, so to find the arc length in parametrics is actually easier than when we were doing it before, I think. All right, because when we were doing it before, we were using the distance formula with like the change in x squared plus the little change in y squared, the square root of that was the distance formula kind of thing. And then we're just integrating that from a to b. Well, we're doing the same thing here, except now it's just dt. And that'll give us the arc length around any sort of weird shape that we want. And we can make all sorts of weird shapes with parametric equations, like this guy right here. What's going on there? Let's see. A circle of radius 1 rolls around the circumference of a larger circle with radius 4. So yeah, here's our larger circle with radius 4. There's that circle. And then we've got another circle, and we fix a point on that circle, and it just rolls around, and that's what happens with the point. It just goes around this other circle as this circle rolls around the other circle. The epicycloid is what that's called, traced by a point on the circumference of the smaller circle, is given by x equals this, y equals this. Find the distance traveled by the point in one complete trip around the larger circle. All right, so that should be from 0 to 2 pi. One trip around, when we're working with cosine and sine, it would be from 0 to 2 pi. All right, so what we need is dx dt and dy dt. And then we can just put it in this formula. So dx dt is derivative of this guy with respect to t. So derivative of cosine is negative sine, so we get negative 5 sine of t times another derivative of cosine. So we already have a negative out front, so that'll make that plus sine of 5t times the derivative of the inside, chain rule, so times 5. All right, dy dt equals derivative of this guy, so 5 sine, derivative of 5 sine is 5 cosine, derivative of sine is cosine, minus derivative of sine again is cosine of 5t times derivative of the inside, which is 5. So there's our two derivatives. All right, so now we just want to square each one, put it under the square root, and integrate from 0 to 2 pi. Or if we want to, it looks like we could integrate from 0 to pi over 2 and then just quadruple it because it's the same thing happening 4 times. But again, that's up to you. So we get our arc length is the integral from 0 to 2 pi this square root, it's going to be a long thing. So this whole thing squared. So we got negative 5 sine of t plus, I'm going to bring the 5 in front, 5 sine of 5t squared plus this guy, 5 cosine of t minus 5 cosine of 5t quantity squared dt. Now, you could just take my word for it, but if we square out both of these, a lot of things do cancel out using the sine squared plus cosine squared equals 1 trig identity. A lot of this does end up canceling out, but we're not going to go ahead and try and simplify that and cancel it out. You can if you want. Practice at home. Give it a try. We're going to go to the calculator. We're going to try and do this on the calculator. All right, since you guys are allowed to use your calculator on everything on the AP exam this year, might not be true in future years. All right, so math 9, we're going from 0 to 2 pi. There we go. And we want the square root of parentheses, and we got to write this whole guy, negative 5 sine of t. Well, I'm going to use x instead. That's okay. I don't have to be in parametric to do this. Plus 5 sine of 5t, or 5x in this case. Oops, I already started the parentheses there. Don't need 2 of them. So close the parentheses for the 5x, close the parentheses for the whole first guy squared. Lots of parentheses happening here. Plus parentheses, we've got 5 cosine of x, close that parentheses, minus 5 cosine of 5x, close parentheses. Then we've got to close the second parentheses, square that whole dy dt. And our variable that I ended up using was x instead of t, so no big deal there. And we get the length around the epicycloid is, I think I killed it. There we go, 40. Well, that's strange, right? It's exactly just a whole number. Cool. All right, so there's our epicycloid length, or the length around this circle rolling around another circle. That's kind of neat that it works out to a nice whole number like that. All right, so that's how we do arc length with parametrics. All right, so that's it for parametrics. That's all we're going to do with parametrics. So if you can do that stuff, you're great. Check out the homework assignment for parametrics.